All right. Hello, everyone, again. And now we're going to do limits involving transcendental terms, but in particular, our next examples will have like sine and cosine terms. So, first one, the limit as x goes to 0 of cos of x plus sine of x over x plus ex. So, here, let's try it. So, you get cos of 0. So, cos of 0 plus sine of 0, all that over 0 plus e to the power 0. So this question is really just testing you on, do you know your basic stuff? Okay, so cos of 0 is 1, sine of 0 is 0, 0 is 0, e to the 0 is 1, so you get 1 over 1, which is just 1 at the end. Okay. That's it for that example. Next example, the limit as x goes to 0 of secant of x. So the first thing you always do when you see one of those evil four others, okay, so you turn them into sine and cosine expressions. So this limit is the same as the limit as x goes to 0 of 1 over cos of x. So secant is by definition 1 over cos. Then you plug your number. You get 1 over cos of 0. So here, cos of 0, be careful. There's actually no problem here. Cos of 0 is just 1, and 1 over 1 is 1. And that's for that one. So by evaluation, you get that. Next one, the limit as x goes to minus infinity of cos of 1 over x. So be careful. A lot of people say, oh, infinity, you said cosine does not exist. It's not cos of x here. It's cos of something else. So you have cos of 1 over minus infinity. Any number over plus or minus infinity is 0. So you get cos of 0 and you get 1 again, just by evaluation. Now the limit of ln of cos of x over e to the power of sine of x. So you get ln of cos of 0 over e to the power of sine of 0. Cos of 0 is 1, so you get ln of 1, and ln of 1 is 0. Down there, you get e to the power of sine of 0, which is 0, and e to the 0, be careful, it's just 1. 0 over 1 is not a problem. There's always that special person who says, no, but 0 at the numerator is fine, so you just get 0. So 4 examples whereby evaluation and using basic laws and, of course, your knowledge of the transcendental functions, you get your answers right away. The next example, we have the limit as x goes to pi of cosecant. Again here, one of those bad four trig expressions. So the first thing you do is you write the actual definition of cosecant, which is 1 over sine of x. Now you plug pi, you get 1 over sine of pi. And sine of pi, sadly, is 0. No. So it's a bad form. What do you do for a division by 0? You need to go left and right. So here we go. Let's first write the left and right. So here, let's compute the limit as x goes to pi minus of sine of x, 1 over sine of x, and the limit as x approaches pi plus of 1 over sine of x. Now you plug in your pi minus, you get 1 over sine of pi minus. Using the graph here, 1 over sine of pi minus is actually 0 plus, and 1 over 0 plus is plus infinity. Now, same thing for pi plus. You plug it in, so you get 1 over sine of pi plus. Sine of pi plus, using the graph here or your calculator, you're going to get a number close to 0 but smaller. So you're going to get 0 minus, and you get minus infinity. Of course, these two limits are not equal. And because they're not equal, then you can say that the limit, the two-sided limit of the original function as x approaches pi of cosecant, does not exist. So same approach. So division by 0, nothing has changed because we have a sine function. You just need to remember how to deal with sine of pi minus and sine of pi plus in this case. Next, we have the limit as x approaches 0 of ln of 1 minus cos of x. So let's try it. So here we go. So you get ln of 1 minus cos of 0. Cos of 0 is 1. So you get ln of 1 minus 1, which is ln of 0. No. So here we have another bad form. Sorry, we have another Indeterminate boundary problem. Ln of 0 is like one of those brand new ones. So you get ln of 0. So you have no choice to go left and right. Okay, so here we go. Again, here, always define your left and right limit first. So limit as x approaches 0 minus of ln of 1 minus cos of x. And then we're going to compute the limit as x approaches 0 plus of ln of 1 minus cos of x. And here we go. So let's plug 0 minus. You get ln of 1 minus cos of 0 minus. Using the graph here, smaller than 0, your output is going to be smaller than 1. So you're going to get ln of 1 minus 1 minus. Ln of 1 minus 1 minus. 1 minus 1 minus is 0 plus. And ln of 0 plus, that's minus infinity. And now let's do it for 0 plus. So you get ln of 1 minus cos of 0 plus. So here, be careful. A number slightly bigger than 0 will give you, again, a number slightly smaller than 1. And then it's the same math here. So you're going to get ln of 0 plus and get, again, minus infinity. Now, these two are actually equal. Okay, so because they are equal, so these two are equal, these two limits, so we both get minus infinity on both sides. So the conclusion, okay, is that the limit as x approaches 0 of ln of 1 minus cos of 0, cos of x, sorry, is equal to minus infinity. All right, for the last two examples, so let's compute the limit as x goes to pi over 2 plus of tan. Again, we don't want a tan here. Ha ha ha, it's no longer summer. Okay, whatever. So here, the limit as x approaches pi over 2 plus of sine of x over cos of x. And again here, one side limit, you plug pi over 2 first. So you get sine of pi over 2, which gives you 1, and cos of pi over 2. No, you get 0. So you get a division by 0. That's bad. So we have no choice to go left and right. Again, here, I strongly suggest that you define them first. So limit as x approach. Oh, sorry, we don't need to go left and right. We're just going to do the right one because this is a one side limit. So we just need to plug in our pi over 2 plus. But now we have the green light to do it. Okay, so I'm just going to rewrite it first. So now you plug your pi over 2 plus. By the way, when you plug the pi over 2 plus, okay, you only are trying to decide, is this 0 slightly smaller or bigger than 0? Like, does it blow to plus or minus infinity? So you only need to plug pi over 2 plus at the denominator. Okay, you don't need to do it at the numerator. Yeah, I mean, if you do it, it's not bad. It's just more work. So sine of pi over 2 is still 1. But where you need to absolutely plug it is down here, cos of pi over 2 plus. This is the part where you have to plug it for sure. If you do it up there too, it's fine, but it's not going to change the answer. It's going to be more work anyway. So what is cos of pi over 2 plus? Again, here, you look at your graph and you will see that if you have a value slightly bigger than pi over 2 plus, this function will blow up to, will be very close to 0, but will be smaller than 0. So this limit blows up to minus infinity. And that's the actual answer. By the way, if you do know the graph of tan of x, you know that there's a vertical asymptote at pi over 2. And you know on the right side, it goes down to minus infinity. So with the graph of tan of x, you could also identify this limit. But I prefer to teach a way where we only require, okay, the graph of sine and cosine. All right, last one. Okay, so last one. Limit as x goes to 0 of sine of x over x. So let's do it. Plug 0 in there. Sine of 0 over 0. Sine of 0 is 0 over 0. Whoa, no. Okay, so you get 0 over 0. That's pretty bad. And here, there's nothing you can do. You cannot simplify. Of course, there's always that special person, okay, that simplifies the x's here. And then you get the limit of sin, but that's a sin. Okay, you're going to be burning in hell. Okay, so you can't do that. Okay, so Here we have no choice, so the limit as x goes to 0 because there's no algebraic manipulation. You cannot factor, rationalize. There's no absolute value. This is not a piecewise defined function. Again, if you're wearing your black belt in algebraic manipulation, you're stuck. You have no choice to start the guessing process with, boom, the numerical method. So here you need two tables, one getting closer to 0 on the left side, one getting closer on the right side of 0. And then once you've done these tables, again, you make sure you do all the tables necessary to finish these questions. You can verify that the best guess, the limit as x goes to 0 of sine of x over x, your guess should be 1. Make sure when you're dealing with limits, there's trigonometric terms, you have to make sure that your calculator is in radiant. All right, this is the end of chapter 2. Okay, so that's it. Bye-bye, lo.